Okay, most of the time, now we have a quiz will mean that we have a quiz, not it's the end of the lecture.
Okay, so let's do one more example. There was a question in the break.
And let's assume we have two spherical shells.
We have two shells, their center is here. One has a radius R1, the other one has a radius R2. The inner shell has positive charge, and the total charge, let's say positive Q. The outer shell will be negatively charged, and the total charge will be
minus Q. So what is the electric field everywhere? So let's start with, what can we say about the electric field? Can we say anything about its general properties that will help us to choose a Gauss surface? There are just two shells. Their center is the same. Although in the figure it doesn't look like that. They have the same center. Two spherical shells. Now, before going that, we know the shell theorem, etc. But what can we say about the electric field that will help us to choose a Gauss surface? We want to apply the Gauss surface, Gauss law. Well, it still has the spherical symmetry. If I rotate my system around this point, in whichever direction we would like, nothing changes, nothing should change. So I have it's just like if I had a single sphere or a point charge, it has the same symmetry. So I know that the electric field should always be in the radial direction, and its magnitude can only depend on the radial distance. It cannot depend on anything else. And if this is the electric field, then the Gauss surfaces are spheres. You can choose any Gauss surface, but if you choose a spherical Gauss surface, it will serve our purpose of calculating the electric field everywhere.
Now let's look at here. We should choose a Gauss surface that contains that point. That's the sphere that contains that point. Let's say this is the region 1, the region 2, and region 3.
We have three different regions.
In region 1, well, in fact, in any region, not necessarily region 1, any region, E dot dA will be just E of R times 4 pi R squared.
And you can just go over our previous derivation. E and dA, they are in the same direction. And well, E is given by this expression, dA is dA times in the radial direction. So the scalar product will be just E times ER, the electric field, times the integral of dA, which just brings me the 4 pi R squared.
Now region 1. Now, if the Gauss surface is entirely in region 1, what is the enclosed charge?
So for this Gauss surface, what is the charge inside my Gauss surface?
There is no charge. So the electric field in region 1 times 4 pi R squared will be 0 over epsilon 0, and hence the electric field in region 1 is just 0.
Again, based on our shell theorem. The electric field in this region should be 0 because it is inside two spherical shells.
Let's look at region 2. If we assume this Gauss surface
in region 2, What is the enclosed charge? It's plus Q.
So this tells me that the electric field in region 2 R times 4 pi R squared is equal to Q over epsilon 0. This is the electric field in region 2 at the distance R is 1 over 4 pi epsilon 0 Q over R squared. And finally, region 3. So we imagine such a Gauss surface which entirely lies in region 3. What is Q enclosed?
Well, the total charge inside my region 3 is I have plus Q charge, I have minus Q charge. So the total plus Q plus minus Q, the total charge is 0. And the electric field in the third region times 4 pi R squared will be 0 over epsilon 0. So the electric field in the third region is again 0. So if you would draw the electric field lines for this configuration,
this is the outer shell, this is the inner shell.
There is no electric field lines inside, there is no electric field lines outside. The only electric field lines are radial and in this region only.
And so this will be our electric field lines.
It kind of resembles the infinite parallel plates in the sense that the electric field is only in between these plates. But the electric field is not uniform, it changes from point to point.
So this is the negatively charged shell. This is the positively charged shell.
Now, any questions? No, the magnitude also. You see, the magnitude is related with the density of the electric field lines. So you see that the electric field lines, they just move away from each other, so their density is being reduced. So if you look at this, since the density is not the same at every point, the magnitude also changes. Not only the direction. And if you look at the expression for the electric field, this is the magnitude of the electric field. So you see that it changes with the distance from the center. Any other questions? Now let's get the motion in an electric field. Now let's get a simple system where we have these almost infinite plates. This is the electric field. And let's imagine we just send a plus Q charge in this direction with some initial velocity v0 in the horizontal direction. And let's say that its mass is m. So what is the force acting on this charge when it enters this field? Q times E.
Let's say this has charge plus sigma, this has charge minus sigma.
So what is E? What's E? The electric field created by these two plates. We can just approximate them to be almost infinite.
So this is Q times sigma over epsilon 0. If this is the z direction, this is the x direction, the electric field is in the minus z direction.
And now we know the Newton's second law,
Which states that this should be equal to mass times the acceleration of the object.
of the charge.
And hence the acceleration of the charge is equal to minus q sigma over m epsilon 0 in the z direction.
So it's just motion with constant acceleration. So if we know the acceleration, we can determine the velocity.
The velocity at the time t will be just the initial velocity times a times the
Time,
which will be v0 minus q sigma over m epsilon 0 times t in the z direction.
this is the velocity as a function of time.
And the position as a function of time will be just r0, initial position, plus v0 times t v0 times t minus q sigma over 2m epsilon 0 t squared in the z direction. This is the position.
Now let's assume that we have such a beam of particles.
We have many particles having the same mass, having the same charge, and they are moving.
And they might have different velocities. And let's say that we want only particles that have a given definite velocity. We don't want all those particles, but we want the ones that have a given particular velocity. How can we extract those using this information?
You see, we have these parallel plates.
Let me just exaggerate the distance a bit. And all of these particles will be following this trajectory, which we know from the motion close to the surface of the Earth, which is another motion with constant acceleration. The motion is always a parabola. The ones that go slow
Will follow this trajectory.
The ones that go faster,
They will follow this trajectory. This is the slow one. This is the faster one.
or
The ones that go even faster, they will follow this trajectory.
so let's say if you want to extract the particles that have this velocity,
Well, the only thing you need to do is to create a hole here. So the particles, they will move faster. They will come here.
once they cross this line, this point, what's the electric field here? Almost zero, so they will just move at constant velocity.
So they will just move along a straight line.
So you have a filter for particles of a given velocity. Of course, most of them will fall over here or over here. The number of particles that's passing through this one will be just a fraction of your initial number of particles, but you know that they will all have the same exact velocity. And the difference in the velocity will be mainly depend on how thick this area is. Because the particles that have a slightly larger velocity will just go through this point. The particles that have slightly slower velocity speed will pass through this point. But if you make this hole small enough, all the particles will have more or less the same speed. And if that is what you want, here you have a device for such a filter. Well, the problem is, how do you create particles having the same velocity, same speed? It's not an easy task. I mean, even when I say that, okay, it's the end of you can go for a break, all of you are rushing out, but all of you are rushing out with a different speed. Any questions? True. Well, because the gravitational force is very small compared to the electromagnetic force. No, in general. If you have, for example, if you take two protons, their gravitational force, well, mass is one factor, of course. If you trust in Feynman, he has this comment that if you and your friend had only 1% more electrons, then the force that you exert on each other would be enough to lift Earth as a whole. Just 1% extra electrons. And well, it will be your homework to verify this, whether this claim is true or not. I mean, just because Feynman says it doesn't mean it's true. You have to test it.
Why is the acceleration constant?
Well, you see, if you look at here, the force turns out to be constant, independent of the position, since they are infinite plates, almost infinite plates. Since the force is constant, acceleration is constant. It doesn't change. Other questions? Okay, let's start a new subject. Well, there is a force we have seen in this example. So it's acting on objects, and these objects can move around like this one. This charge is moving around. So if there's a force acting on an object which moves, then we can talk about the work done by the object.
So let's remember the work done by a force we had this general expression that was F dot dl from the initial point to the final point. So you have this object moving around along a path. So you start from the initial point, it goes to the final point. It might have some mass m. There is a force F acting on it.
So in this case, this was the expression of the force, of the work done on the object. So what you do is you divide this line into very small segments. At every segment, there is a displacement dl. There is the force acting on the object on that segment. You take their scalar product, that is the work done on the object during that segment. You just sum over all the segments, so you calculate the work. Then we had also defined classified forces, if you remember in 109 in mechanics courses, that the forces we called sum of the forces conservative forces. F is conservative if this work done, and we had said that in general the work done by a force depends on how you go from the initial point to the final point, but there is a special class of forces for which this work done is independent of how you go from the initial point to the final point, and those forces are what we call the conservative forces.
if the work done is independent of path.
So if there is a force, and if you take an object from some initial point to the final point, if the work done by that force doesn't depend on how you go from the initial to the final point, that is a conservative force. Now, some of the examples that we did was, for example, the gravitational force. If you just take this object from this point, and if you just move it to this point just like this, there is some amount of work done. Or if you just take this object and move it around and bring it over here, there's some work done. And we know that since gravity is a conservative force, the work done on this object by gravity, not by my hand, by gravity, as it just goes around here, is independent of the path. So gravity is a conservative force. Now we had also seen that the Newton's law, the gravitational force on the Newton's law, is a conservative force. Do you remember the derivation? The gravitational force between two masses is a conservative force basically because it's only pointing in the radial direction all the time. It doesn't depend on the velocity, etc. It's always in the radial direction and depends only on the radial distance. So that's based on those things you can actually prove that the Newton's gravitational law is a conservative law. But the same is true for electromagnetic force, electrostatic force, the Coulomb law. Coulomb law is always radially outward, and it only depends on the radial distance. It's a conservative force. Now the proof, I will not go over the proof, but I will just remind you some of the main steps. So let's say you take this charge plus Q, it is fixed, and you take some Q prime charge here and move it from there to this point along such a path, or move it along, let's say, this path. To prove that the work done if you choose the first path or the second path is the same, what you do is you just imagine such circles or spheres. Now the work done along this path, or let's say you divide each path into a broken path, you approximate them by a broken path. Let's say you start from this point, you start from here, take a circular part, then a horizontal part, then another circular part, radial part, circular part, radial part. So if you just draw these circles smaller and smaller, this broken path will be equal to the actual path. Now you can do the same thing for the other path. You can go here, then in this direction, this direction. So this is another broken path that approximates this one. Now the trick is the work done by, let's say, this path and this path, these two paths, they're equal because the force depends only on the radial distance, and it's radial. These two are radial segments. And there is no work done on the horizontal paths. So if you just sum the radial parts along this one and along the other one, they turn out to be equal. So that's the main steps of the proof. And if you are interested in the proof, just review your mechanics course. I will not go into too much detail. Question? Okay. So it's a conservative force, the electric force also. So that's kind of nice. That tells us that if I go from the point A to point B to point B, and if I calculate Q over 4 pi epsilon 0, Q prime 1 over the distance, cubed R minus R prime, dot dl. Well, this is the force acting on the charge Q prime. this is the force acting on the charge Q prime, and I'm just imagining some path connecting A to B, and this is the work done on the charge Q prime by this force, and this is independent of the path. Since it's independent of the path, it only depends on point A and on point B, and not how I get from point A to point B.
And this function, this integral, we define as VA minus VB.
And VA is the potential energy of the system when the Q prime charge is at the point A. And this is how we had defined the potential energy for a conservative force in our mechanics course. For an arbitrary force that is conservative, we can define the potential at a given point.
VA, this was minus F dot dl plus VB as you go from point B to point A.
This was the general definition of the potential energy of a given system. And in this particular case, we have the Coulomb force acting between the charges, so this is how we define the potential energy of the system. This is the electrostatic potential energy. Now the force, we said that in the case of the electrostatic force, we define the force as the charge times the electric field.
So VA is equal to minus from B to A Q prime times the electric field at the point, electric field dot dl plus V of B.
So if I divide everywhere by Q prime,
so this Q primes cancel, and this is what we call the electrostatic potential. You at a given point is nothing but the potential energy.
if I would put a test charge Q prime over there,
divided by Q prime, which is minus from B to A E dot dl plus V of, or U of B.
So this is how we define the electrostatic potential at a given point.
By the way, this is not equal to the electrostatic potential energy.
This is the difference between them. This is the electrostatic potential energy. If you divide it by the charge, your test charge, what you obtain is the electrostatic potential and electrostatic potential at a given point. You say the potential energy of a system is, in a sense, the energy that you can extract from the system. So the difference in the potential energy of a system is the energy that you have extracted from the system or you have given to the system. Now, the electrostatic potential Potential is not an energy. It is, if you put a test charge at a given point, and if you know the electrostatic potential at that point, now when you multiply the potential by the charge, then you can obtain the potential energy.
What do you mean by saying that electrostatic?
This is what I mean by when I say the electrostatic potential. The potential is just like electric field was the force per unit charge. If you put a unit charge there, the electric field would be the force. Electrostatic potential is the electrostatic potential energy per unit charge. So it's joule per coulomb. What do you mean? Electrostatic potential and electrostatic potential energy, they are different things.
Equation U equal UV. Which one of them is the potential energy and which one is the potential? U or V?
U is the electrostatic potential. Well, at least in this derivation, I use U to denote the electrostatic potential. V I use for the electrostatic potential energy of the system. In these lines.
U is the potential, V is the electrostatic.
Here, U is the potential, V is the potential energy. Potential is the energy per unit charge.
We can define potential, electrostatic potential, we need yani Q plus.
Well, you see, to measure the electric field, what we did was we put some test charge. We calculated the force acting on the test charge and divided that force by the charge of the test charge. That's how we calculated the electric field. You can do a similar thing here. You can put a test charge somewhere, calculate the potential energy of the system with the charge over there, and then divide that potential energy by the charge of your test charge. Do we have? Well, okay, the conventional symbols will be, V will be for the potential and U will be the energy. I confused. But the names are not important. What is important is what you mean. We will be spending our next week on studying the potential and the potential energy difference. So this was just kind of the preliminaries so that you will have at least now a very slight concept that we have these two slightly different things, potential and potential energy. Okay, so see you next week.